Okay, so any questions about things? Okay, so let's go ahead and go. Okay, so I'm going to back up a tiny bit at the start of reactions. Now, whenever we have a double bond, it's unstable. It wants to react. Now, there's a lot of ways that double bond can react. One way is addition reactions. That means a molecule, a diatomic molecule, is going to lay across that double bond and add to it. And there's two kinds of additives. There's a homogeneic one, like that would be homogeneic. And then there's hetero. Yeah.
It's supposed to be Miss Kirkpatrick's class. This is a Miss Kirkpatrick's class.
This is chemistry.
Okay, you know where nutrition is? That's
Yeah.
said it was gonna be in here this week. Last week.
It's at 105, we'll switch class. So
Yes, we switched rooms.
right now.
I appreciate you.
Yeah, last one on the right.
Okay, thank you.
So nutrition people need to be in room 105.
I think I'm the only one. It's a,
We just did it like last week, so. This room was over too many people in here, although it's pretty full now. Okay, and whenever you have a heterogeneous additive, it's going to expect a mix. When you have a homogeneic additive, there will be no mix. It'll be just one product. Okay. All right. So this here is homo, the H2, Cl2, again homo. This is hetero here, and this is hetero. Now, sometimes you don't have a mix, even if you have a heterogeneous additive. Most of the time you do them. If your product is small, that's when you usually don't have a mix. Anything longer than 3 carbons on the product side, you'll have a mixture. Okay. So because alkenes are unstable compared to alkanes, this reaction goes fairly well. And what happens with the homogeneic ones, we have each side of that additive is going to bond to each side of the double bond. And because it's the same, remember what this happens, there's a 50-50 chance of that chlorine Cl2 hitting the double bond. Get it this way or this way. But because it's Cl on both ends, there's no difference between the two. There is a difference, you just can't tell the difference. Now, the only one is a little different on this is when you're adding HH across the double bond. It's a pretty slow reaction. So what they do is they add a catalyst. That catalyst is usually platinum. And platinum is even more expensive than gold right now. Gold is at $5,500 an ounce right now. Platinum's more. Now, whenever you get a mix, you have to determine the stability of the mixture. Which of them is more stable than the others? We have two tests for that. One is symmetry, the other one is Markovnikov's rule, where we have the most terminal hydrogens is more stable than one with the least amount of terminal hydrogens. So you need to do the test both times. Okay, for example, on this one here, we have 3 hydrogen on this, on the end here on the right, 2 hydrogens on the left. That's 5 total. If the double bond is in the middle, we have 3 and 3. It makes it 6. So Markovnikov rules that the bottom one is more stable. Also, the bottom one is more symmetrical than the top one. So both those lead to the one on the bottom being more stable. Circle it. And usually you get something like a 60-40 mix. Now, here's the first example of a heterogeneric additive. This happens to be hydrochloric acid. And if we were to this then would add here and here. So it's going to hit it 50-50 times. So what you end up with is so Markovnikov's, we've got 2 hydrogens, 3 hydrogens, 3 hydrogens, 3 hydrogens. So Markovnikov, it's got more terminal hydrogens. So Markovnikov says it's more stable and also it's more symmetrical. Now, when you're doing reactions, all I've done so far is starting with a product, conditions, excuse me, I've started with reactants, conditions, and you generated a product. Sometimes I'll say, how do you make this? So you have to figure out what you need to start with then, and the conditions. So you're gonna be going both ways. For example, if I wanted to make no, let's not do that one. How would I make that? 2 ways to make that. The easiest way is with coming from a double bond. So, same backbone. That's 1, 2, 3, 4, 5, 6. 1, 2. Okay, 6 carbon backbone. And if we have a double bond here, and add HCl, that HCl is going to lie across that double bond. So that means we're going to get a mixture because it's a heterogeneic additive. But one of them you end up getting is what we want. We could have also done it that way. You do it this way, you're going to get this plus this. It's just going to lie across that double bond, two different ways. Okay, does that make sense? So half the reactions on the test will be, how do you make this? The other half are going to be, if I have this under these conditions, what do you end up making? Half and half. Now, the dry lab lets you practice that. Also, if you have purchased the textbook, there's some examples in your textbook as well. In the chapter on alkenes. Okay, so does this make sense? Now, when I say does it make sense, you can follow me, right? Doing it on your own is a level up. Definitely a level up. That's standard with all problems. Okay, so I'm going to do lots of practice with you guys, examples. Okay, water, if you think of water as H bonded to OH, that's a heterogeneous additive again. So we're going to expect a mix. That's one way you can make an alcohol. Alcohols are a compound that's got an OH on it. Like drinking alcohol with ethanol, it's a 2-carbon alcohol. Rubbing alcohol, 3-carbon alcohol. Formaldehyde, not formaldehyde. Methanol, 1-carbon alcohol. Very common alcohols. Carbohydrates are also alcohols. Frequently you'll see added sweeteners as polyols, alcohols. And you know what ethanol does when you drink too much of it? Too much sugar will do the same thing to your brain. It doesn't make you drunk though. It has the same effect on your body organs as drinking alcohol. And if you drink methanol, the 1-carbon alcohol, that leads to blindness. It's very bad for you. Moonshine frequently is adulterated with methanol because their distillation apparatus is very crude. So just FYI, White Lightning, do not buy.
What would happen if you drink sparkling water? What would be the effect of drinking sparkling water?
Sparkling water has carbon dioxide in it. Carbon dioxide in water forms carbonic acid. And carbonic acid isn't very stable. So it gives off, that's the disease, the carbon dioxide. Perfectly fine. Much better than wine. Guess what I had last night for my dinner? Wine. Well, I went to a really nice restaurant. It's Antonis, across the street from Corey Brothers. If you ever have a special event, their food was excellent. I'm really picky about food. Look a lot myself. It was really good. Nice service. It was. In fact, my friend ordered pork chops. I never order pork chops. They're always tough and dry. His pork chop was the best I've ever tasted in my life. It was tender, it was juicy. Oh, it was really good. So, okay. All right. So one way to make an alcohol. Now, one subunit we're going to have is alcohols. That's the next one after alkenes. So we're going to learn a lot about alcohols. But anyway, to make an alcohol, one way is to take water with an acid across a double bond. You create an alcohol. All right. So that's the reactions for alkene. Now, there are more reactions because some of the other things come from alcohols. For example, an aldehyde or ketone is made from an alcohol. In fact, your body detoxifies ethanol in your liver by creating an aldehyde. And then aldehyde is then further reacted to form acetic acid, and that's how it eliminated out of your body through your urine. That's also how a breathalyzer works. It checks for ethanol, oxidizes it to the aldehyde, and creates a color. The darker the color, the more alcohol. Okay. All right, now. There is a particularly stable molecule, 6-carbon cyclic molecule that has 3 double bonds, 3 single bonds. And they alternate, single, double, single, double, single, double. Benzene is extremely stable. Very few things react with it because it's so stable. Let me tell you a story. When I was teaching high school in the 70s, Sacramento High School, when it was a real high school, I used to take my students over to Davis on field trip to the environmental toxicology lab. That's where my wife at the time worked. And we would go through all the professors in that department and they would talk about what they're doing and stuff. It was really very cool tour. One of the people, his specialty was mycotoxins. Those are toxins that come from fungi. So this was his presentation.
Even includes mushrooms also that has fungi.
Say again?
Does it include mushrooms that have in the fungus that's included?
That's why I don't eat moldy bread. Well, this was the presentation the guy did. He talked about fungus and the toxins produced by fungus, etc. And then he took a beaker of benzene. And then he explained how stable benzene is. Doesn't react with anything. Then he drank it. He literally drank benzene. And he said it's going to go right through my body, out the back. Which is true, except for one problem. Benzene, because it's so stable, goes in between your DNA. It sticks between the spirals. It's like throwing a wrench into a transmission. Messes it up big time. Hence, benzene is a carcinogen. Now, it was classed as a carcinogen in the 80s. I was over there in the 70s where he was drinking benzene. And guess what he died of? Cancer. So anyway, there's a lot of benzene in gasoline. One of the byproducts. Burns really well, but there's benzene in. So when one of the reasons when you pump gas, all that fancy sealant is to prevent things like benzene from getting out into the air. The benzene is really an interesting molecule. Okay, anything with benzene in it is called aromatic. It also includes fused benzene rings. So I had. Now, the other way to write it is like this. And 99.9% of the time, that's the way it's written, with a circle in the middle. Okay, so this is considered aromatic as well as that, etc. Now, when you burn wood, like in your fireplace or a campfire, you produce something called creosote. Creosote is aromatic. And by the way, carcinogenic. The reason why they found out that it was carcinogenic are the chimney sweeps in the Midwest were having abnormal amounts of bladder cancer. And they did some research and they found out it was coming from the creosote inside the chimney. So if you burn wood in your chimney, don't clean it yourself. Have someone who's trained on how to minimize the danger of creosote. Also, don't be in the house when it's clean. It's just really bad stuff. Okay, so there's two basic compounds. Aromatic compounds contain benzene. Aliphatic compounds don't contain benzene. And we are not doing bond hybridization. Now, the reason why they put a circle in the middle is because notice where the double bonds are placed here, and it goes back and forth. And that's why it's more stable than just a plain old double bond, because it spreads out that instability over the whole molecule, where a plain double bond doesn't. Now, there are few benzene derivatives, simple benzene derivatives. In other words, when a add-on substitutes for a hydrogen, then the base name is benzene there. So we have ethylbenzene, nitrobenzene, bromobenzene, and chlorobenzene. However, this is what's weird about aromatic compounds. Well, before I go on, there are some specialized benzene compounds that are very common, and IUPAC has allowed the common name to be used. So, for example, like methylbenzene is also called toluene. Hydroxylbenzene is normally called phenol. You've probably heard of phenol. It's a very common chemical. Common in wine, it's common in beer. It's used as an antiseptic. Bless you. It's used a lot. Very common. Aniline, that's a unit 3, but it's amino. And then if there's an acidic group here, it's called benzoic acid. So for right now, for this unit 1, know those two, phenol and toluene. Now, if this is an ethyl group, it's not toluene, only the methyl group. Okay. When the benzene ring is not singly substituted, like up here, where it's a branch, the branch isn't named benzene anymore. It's called phenol. Like this is a backbone here. Seven carbons long, and if we count from right to left, left to right, it's the same carbon number 4. So that's for phenylheptane. And no word benzene in it at all. Here. Okay, we've got a cyclic butane with two benzenes as a branch. So it's going to be 1,1-diphenyl cyclobutane. Now that messes a lot of people up. So basically, the only time you have benzene in the name is for the simpler versions. Now, when you have two substitutions on the benzene ring, it's still called benzene, not phenyl. Now, there are two ways to name these. One way would be, this one here would be 1,2-dibromo benzene, or ortho, shortened to an italic O, dibromobenzene. Meta, think of middle, meta. So this would be a 1,3 dibromobenzene, and this is para dibromobenzene. I frequently on tests ask you to give me two names for a benzene compound. So you first say, like on the one on the far right, para-dibromobenzene or para-chlorobenzene or parabenzene. The ortho, meta, para are holdovers from the alchemy days, but we still use them a fair amount today. Now, if you have three substitutions, there's no ortho, meta, para. You just have to name it. Yeah. Say go up to this one. You have it? Okay, aromatic compounds are very similar to plain double bonded alkenes and alkanes. You know, they're flammable, they're nonpolar, all that stuff. The main thing about aromatic compounds is their stability. Now, aromatic compounds are ubiquitous. They're all over the place. Biochemically, you'll see them a lot. Organically, you'll see them a lot. Industrial, agricultural, food industry, they're just all over the place. Again, because they are so stable.
We need to learn the key terms also on top of the, when unit one test, we have to learn the, key terms. Like, the name of the key terms for unit one. Yes.
I'm from unit two. Yeah, one, about that later on. You just have to know the ketone, you know, the name of it. There is a name for it. That's your ketone.
But for unit two, we don't have to learn the key terms.
And there's ketones and aldehydes, they're very related. What is in the middle and what is on the, aldehydes on the end, ketones are, the carbonyl group is on the, is in the middle. All these are part of Freesoap. All these are very, very stable, and they're all carcinogenic. Okay, so that's it on the chapter on alkenes and aromatics. So let's go through some reactions now. Okay, so these are all the unit 1 reactions. Now, whenever we produce carbon dioxide and water, that's the product of combustion. Everything in unit 1 is flammable, burns. And it burns, assuming there's enough oxygen, it burns to carbon dioxide and water, like your car. Gasoline, when it burns, converts to energy, which turns the motor over, plus carbon dioxide and water. If you go out in the morning, start your car, and run around to the back, you'll see water dripping out of the tailpipe. That's because water is a product of combustion. After about 10 minutes or so, there's no more water dripping out. Why is that?
Because it's not gas.
Who said that?
It's burning gas.
Yeah, it's steam. It's still there, it's just not liquid, it's gas. It's pretty cool. Contrails on jets, when you see a jet up high, not just taking off, but when a jet is up high, you'll see a white trail behind the jet. Anyone know what that is? Called a contrail, but what is it? Okay. Jet fuel is similar to diesel. When you burn jet fuel, you produce carbon dioxide and water. What do you think that white stuff is coming out of the back of a jet up high? And, that's right, and two things. Water. Okay, 30,000 feet these jets fly at, sometimes 40,000 feet. It is cold. What happens when the water gets cold? Freezes to what?
To ice.
Ice crystals. Ice crystals are super fine and comes out, so they float up there. So that's what a contrail is. In World War II, the latter part of World War II, sometimes Germany would be bombed by 12 to 1,500 B-17s and B-24s. So the whole sky was covered with contrails. And they're all going every which way because they're being chased by German fighter pilots. So you can see those bombs coming way off, So. Okay, so everything that, oh, it requires a spark also. It just doesn't happen spontaneously, unless your garage is really hot. Gee, does it get hot around here? Okay, so here we are. So if we start with, remember now, the arrows. Okay, so let's take propane. Okay, so this is the arrow points to the product. And the tail is attached to the reactants. So the arrowhead, products, tail, reactants. So that's how to interpret this flowchart. So if we want to make an alkane, we have to find an alkane that has an arrow on it. Like that. Okay, and how do you make it? Go backwards on the arrow to the tail, and the tail is how you make it. So if we were to make a alkane, we'd start with a what? An alkene. And what would you do? These are conditions. We'd add H2, homogeneic, generic, added in, plus a platinum catalyst. That'll give us the alkene. So use the arrows to your advantage. The arrowhead is the product, the tail are reactants. So if you're going to make something, find where it's attached to the arrowhead. If we want to make an alcohol, how do we make an alcohol? Well, we find where the arrow tail is. The tail is attached to the alkene. So that means we can make an alcohol from an alkene. We can do that by adding water and an acid. The common acid in organic chemistry is sulfuric acid, H2SO4. But if you just see H plus on your dry lab, I believe it's designated as H plus. Because my colleague, he and I were making these, he liked H plus. He said any acid will work. Sulfuric acid, hydrochloric acid, nitric acid, all those acids work fine. So why put down a specific one? So you'd always put H plus down. This guy was interesting. His wife was a neurospecialist. And they each had their PhDs. And his wife had not only a PhD, she had an MD. So she was an MD, PhD. Heck, I don't know what they talked about at dinner, but pretty wild. Okay, another example. We wanted to make notice there's another way to make an alkene. I'm going to cover this when we talked about alcohols, but we can make an alkene from, oops. From an alcohol. Okay, so let's practice this now. Okay, say we want to make I want to make that. So what is that? Now, whenever we do a reaction, there are some steps for full credit. Name the reactants, products. And name the most stable product. Okay. All right. So we want to make this, what is this? This is a 1, 2, 3, 4. So this is a butanol. It is a 1-butanol. And that's when we talk about alcohols, I'll show you how to name alcohols. All right. So we want to make an alcohol. So let's find an alcohol on here. Okay. And how do we make an alcohol? Well, alcohol's head here. And we follow the head up to the tail, and it's an alkene. So that means that alcohol is going to start from an alkene. So that's 1, 2, 3, 4. So we're going to start with the same backbone. And alkene. So where's the double bond going to go? Well, there's only 2 places it can go. It can go here or there. So which one are we going to use? Top or bottom? Now remember, the OH is going to attach on either side of the double bond. So if it attaches here or here, with this one down here, it's going to be here or here. So which one of those are we going to start with? Top or bottom? Which one? Top, correct. Because the bottom one doesn't yield anything with a terminal OH group. So we're not going to start with that. And remember now, when we add water across the double bond, we get a mix. So if we start with this now, what we're going to do is so the OH is going to add 50% of the time one way, 50% of the time the opposite way. So one of the times it's going to be this. Okay, so we don't want that though. But you're going to get some of that because you're going to get a mix. So the job of a synthetic chemist, for example, when we in lab synthesize aspirin, we're going to have impurities along with the aspirin. So then we have to purify and get rid of the impurities. So when we made this chemical here, this 1-butanol, we have 2-butanol as an impurity. So we have to then purify our mixture and get rid of the 2. This is 2-butanol. We need to get rid of that 2-butanol, the impurity. So that means it's further refinement. Now, when you buy chemicals, you go to the hardware store and buy root killer. That's copper sulfate. And it's loaded with impurities, but it's also cheap. If you go to a fancy analytical chemistry supply house and order analytical grade copper sulfate, it'll cost 100 times what the root killer costs because it's very, very pure. Okay, so we have to name reactants and products. Okay, that's 4-carbon alkene, so that's going to be 1-butene. Conditions are water and acid. And our product is named 1-butanol. Between the two products, which is more stable? The 1 or the 2-butanol? Well, let's look at the 2-butanol first. Terminal hydrogens, we have 3 and 3. Three and 2. Okay, Markovnikov says we have more terminal hydrogens, so it's more stable. Symmetry. This is the one on the left is all one-sided. One on the right is more balanced. So symmetry and Markovnikov win. That means if we were going to make 1-butanol, we're going to have a whole bunch of the other product impurities we need to get rid of. But it's going to be the more stable product of the two. So we may get a 30-70, 40-60 mixture. Okay, so does this make sense? Okay. Yeah.
I'm just confused on why we marked that off, but then you still chose the 2-butanol. I got lost somewhere in the process.
Okay, you're gonna have a mixture. And what's the mixture gonna do? Well, the OH is gonna be on either side of the double bond. That's why we're gonna get a mixture. And then the next one is, well, in the mixture, which one of these do we want? We want this one. Okay, yeah. But unfortunately, it's also more stable. It's still an impurity, and that's something we're trying to synthesize. So, ask me your question again.
So I was just answering, I was just wondering so there's both different answers to different questions. Like you're circling the most stable product within the 2-butanol, and then you think we're 1-butanol to say it's
First
correct
of all,
part of
it's the first question. How do you make?
Oh,
We make it starting with the alkene. Unfortunately, when we make it, we have a whole bunch of this. Now, in the test, if I ask you that same question, I'm looking for that. And if you want to put this in as extra, that's fine, but I'm not marking you off if you don't put that.
okay.
But this is really what's happening.
And then I was also just wondering, how did we go from how we got the 2-butanol?
Going back to the alkene. The water is going to add across the double bond this way and this way. So one time it's going to be on the left, the other time it's going to be on the right of that double bond, just statistically, because everything's moving around. when it hits, they run into each other, reaction is gonna happen. But it's 50-50. That's why we end up with a mix, because it's 50-50. That's why you have to put the double bond in the right place, so that one of the hits is what you're trying to make.
Cool. So, I'm sorry, but just to clarify, like, so the first step we would do is write the reaction and their name. And then in order to find like the impurity or the mix, we would use the product.
And then we use the two sets, the Markovnikov test and the symmetry test. And sometimes one won't work at all. Like symmetry, sometimes they both look as off symmetrical or unsymmetrical as the other one. You just ignore that when I look at Markovnikov. And if both of them fail on both, just not determined, and determine which is more stable. And I'll try not to put those kind of problems on the test. I want to make it clear which is more stable.
And the terminal hydrogens, they had to be symmetrical as well, like if you had 3 hydrogens, you can use 3 hydrogens on.
Doesn't have to be symmetrical with Markovnikov. You're just looking for numbers. 5 versus 6. It doesn't have to be symmetrical. The other part, the symmetrical one, that's just eyeballing. Which is more balanced? Which is more lopsided? Lopsided is less stable than something that's. Nature loves symmetry. More than not symmetrical. Remember in your 305 when you're doing subshells? Remember, did you go into when you have a full subshell versus a half subshell versus lopsided? And the full one or half filled one are more stable than the ones that are lopsided. And again, it's a symmetry issue. Cool. All right, let's do another one here. Let's do one more, then we're gonna get into alcohols. Okay, okay, so let's make this. Okay, so let's name it. It's a cyclohexanol. Six carbons, cyclic, and alcohol on, we're gonna call that carbon number 1. Okay, so head of the arrow is alcohol. Head of the alcohol can come from an alkene. So which alkene are we going to use? The same backbone. So what are we going to use? Which alkene are we going to use? You also need water and acid there for conditions. But which alkene? Anyone got any ideas? Yeah. Um. Yes and no, mostly no. Benzene's got, is now clean. I mean, it's got double bonds now. But the problem with benzene, it's super stable. And where do we at? So instead of benzene, we're gonna use what? Think of benzene now. What if benzene made up of single and double bond, right? Single, double, single, double, single, double. If we didn't have three double bonds in there, just one, then it becomes really reactive, not stable anymore. A single double bond. Now when we put water across that, we're gonna get two products, depending on which way the water lays across the double bond. So we're gonna get this and that. Now, what's the difference between left and right on the products? The different carbons, but overall, do they look like the same molecule? Why don't they look like the same molecule?
Different placement for OH.
Now, this is not a good question. These molecules are moving around in space. Okay? One of the modalities of movement of molecules is from one place to another, called that translation. There's vibration, rotation, translation. Those are the three modalities of movement of molecules. So if we were to take that molecule on the left and twist it a little bit, it looks just like the one on the right. They're the same molecule. So we don't have a mix. Okay, so we need to name the reactant. So product we already named. So this is going to be cyclohexene. And you can name it one if you want. And then you just name the carbon where it starts as one. So we name the reactants, conditions, water plus an acid. Products are cyclohexanol. Okay, so we're going to start alcohols now. So the alcohol chapter is gonna have three parts to it. Aliphatic, aromatic, and something called an ether. Okay. Okay, so alcohols are COH. Ethers are COC. And both of these can be either aromatic or aliphatic. Now, frequently in textbooks, they use the R. The R is some generic carbon chain. R prime is a generic carbon chain, but not the same. R double prime is yet another carbon chain that's different than the first two. So R is just some group attached to it. So we have, for an ether, we've got R, and the thing that attaches to the O is a C. So the R's can be anything as long as there's a carbon attaching to the oxygen. Same with the alcohol. We can go ROH, and again, the R is anything as long as it's got a carbon being attached to the oxygen. The other term they use for R is alkyl. They'll say an alkyl group. That's just any organic compound. Very generic. So all these are alcohols. Why? Because they have hydroxyl groups. And one not included on here is a carb. This happens to be glucose. Now you're going to learn these really well in Unit 2. That's glucose. Notice there's a whole bunch of OH groups on it. So it's a special kind of alcohol. It's not a polyol necessarily. It's a polyol and some fancy word called a hemiacetal. But bottom line is it should be on the list up there as well. So alcohols can be extremely simple, like methanol. Methanol is a 1-carbon alcohol. Ethanol is a 2-carbon. Propanol is a 3-carbon. Isopropanol is also a 3-carbon. That's rubbing alcohol. Menthol is not the same as menthanol. They almost sound the same, but they're very different molecules. Menthol is used frequently in cigarettes make them smell good. They're also just as bad carcinogenicity wise as all these other regular tobacco. My mother used to smoke menthol cigarette. Used to think they're better for you. It has a kind of a minty smell. All of you have heard of cholesterol. Cholesterol is a rather large molecule. It has tiny OH group on it. Still alcohol. So it'll behave like an alcohol in reactions. Alcohol naming. Okay. The OL in alcohol is the functional group name for alcohols. So, naming is in three parts. Branches, backbone length, functional group name. Okay, so we have an alcohol, let's name it. Backbone. Looks like we have a branch. Now, the backbone numbering, it has to do with the functional group, not the branching. So if we start on either side, let's do this differently. Let's do that. Okay. So the OH is closer to the left side than the right side. So we're going to start numbering on the left. Okay, 6 carbon backbone. So it's going to be a hexa alcohol, OL, and a branch on carbon number 4. And what carbon is the OH on? Carbon 3. So 4-methyl-3-hexanol. So it's just like all the others, 3 parts. First part on branching is optional. If there's no branching, you can leave that off. Okay, cyclohexanol. And there's a branch of carbon number 2. Now, the reason why I started carbon number 1 on where the functional group was, it's standard practice to do that. On a cyclic, anything, if you got a functional group attached, that's going to be automatically carbon number 1. Then we can name clockwise and counterclockwise. If we number clockwise, you're going to get the lowest number on the branch. If we go counterclockwise, it's going to be 5-methyl cyclohexanol. Now, if you want to put a 1 here, just to be consistent, that's fine. It's not required though. So are there any questions about naming alcohols? Yeah.
What if we had two, two hydroxides? You'd be like dicyclohexanol.
Okay, so we have multiple ways to do this. So this is gonna be a diol, di meaning two. So it's gonna be 1, 2, 3, 4, 5. So it's a penta. So this is a 1, 3 pentadiol. That makes sense, the way it's numbered? Yeah.
Alzheimer.
How can
Very
we,
simple way to tell the difference between them all. To know for sure, like, which one's an alcohol, like what we're looking at. Does that make sense? My question doesn't make sense.
we do two things. I'm not sure I follow, and also speak up. Remember, I'm like your grandfather.
Is there an easy way to like differentiate between like what's an alcohol, what's an alkene?
It's the functional group.
Okay,
And in this case, functional group makes it an alcohol, the OH.
Okay.
And the fact that it's got a double bond means it automatically makes it an alkene. Now, challenge comes in, well, what if we have both of them? Then you'll end up with an enol.
okay,
And that's frequently found in nature, when nature wants to move one thing to another. They'll go to an intermediate. Frequently, they are enols. And that's not enzymatic. And but going back to your original question, the functional group determines name. Okay? There's one functional group on there. That's the name. If there's more than one, then there's a priority system. They have, for one functional group is more important than the other. And if you look in your lab packet, dry lab 2. The last page of dry lab 2 is that hierarchy. I'm going to talk about that in a minute. So the simple one is, you have one functional group that determines it.
Are we ever gonna get the one with enol of all of them? Or are we gonna be tested on the one with all of them?
Of all of them?
Yeah, the enol one that you said?
No. No, I don't think it's within the scope of this. You were in the year-long class, oh yeah. Be all over. They don't do biochem, they have to split between biochem and OChem. They don't do any biochem.
That one more is math based.
No. No math in there. They do something called mechanism stuff, which is how things work at the electron level. And we don't do that. And the converting mechanisms there. It's in the PowerPoint slide by Skipper.
Oh, okay, that's the orbital.
That's bond hybridization. I skipped that too. It's just a. That's the reason why carbon has 4 singletons and not 2. When you went into your 1s, 2s2, 2p6 stuff, 305. Well, carbon is supposed to have 2s2, 2p2, but it doesn't. It has 4 sp3s, which are singletons. And the reason why that happens is more stable than the one, because otherwise you should only have 2 bonds. But it doesn't have 4 bonds. Why is that? That's with the bond hybridization. And don't write any of that down. Okay. That was a good question on multi-hydroxyl groups. In fact, it's covered right here. Now, aromatically, we have an aromatic, the simplest aromatic alcohol is phenol. Or hydroxylbenzene. Okay, phenol is the preferred name. Notice OH is always carbon number 1. And then base is the common name phenol. Now, this is something important. The reason why it's important is because the reactions will be different based on where the OH is located on the molecule. And it's in relation to the number of hydrogens that are on the same carbon as the OH group. Now, let me show you what that means. Let's count hydrogens. Okay, so the terminal end's got 3. The middle carbon got 2 CH and 2 CC bonds. And the terminal on the OH end has 2 hydrogens attached. If it's in the middle, got 1 hydrogen, not 2. Okay, if it's in the middle with another carbon branch off from it, it has no hydrogens. So if it's got 2 hydrogens on the carbon, it's called primary. It's got 1 hydrogen secondary. Now, this is important because when we oxidize an alcohol, there are 3 different ways it can be oxidized, depending on the number of hydrogens attached to that carbon with the OH. Now, if you remember from 305, oxidation is the loss of electrons. In organic chemistry, instead of electrons, we talk about hydrogens. So oxidation is the loss of hydrogens in OChem. All right. So primary, secondary, tertiary. Guaranteed, I'm going to ask you what class of alcohol is this structure on the test? So make sure, and it's really important, to understand the difference between the primary, secondary, tertiary. Because you'll get different reaction products with each one. Another thing that's particularly outstanding about alcohols is they're extremely polar. That's to do with that oxygen. Oxygen is very electronegative because it's on the top right of the periodic table. That makes it very soluble in water. For example, vodka. Vodka is a mixture, 50-50 mixture of water plus ethanol. Can you tell the difference between the ethanol and water in vodka? Looks just like water. So it's very, very soluble in water. It almost looks like water. Water's got an OH group in it. Alcohols have an OH group. Like dissolves like. Alcohols are very strong in molecular force. That means the boiling point is much higher than a comparable weight alkane. Huge difference. Also has higher melting point. It also has a higher surface tension. But remember, like dissolves like for the rest of your life. It'll help you when you're in the kitchen cleaning. For example, if you want to clean grease, you don't use water. You use something like grease, like for example, gasoline works quite well cleaning grease. But I wouldn't recommend using gasoline in your kitchen. Using something more safe. But gasoline, because it's like grease, dissolves it really well. When you're cleaning your windows, there's two kinds of spray you can get.
That's blue. When that's blue. Like cleaning the glass. Yeah, Windex.
Like Windex, that's just, oh, okay, make it free. As no cleaning function at all. Kind of like white. Okay, you clean your windows. Your windows get greasy if it's by your stove. So you're going to use a cleaner that dissolves grease. Usually has ammonia. The Windex comes with and without ammonia. The one with ammonia is around your stove and your hood over the stove when it gets greasy. But windows, if they're not around the stove, aren't greasy. They require a non-ammonia cleaner. That's why Windex comes both ways. One with ammonia, one without. I was telling you before that bug spray I invented with ammonia in it works extremely well. Extremely well. It leaves no residue, totally safe, and it's cheap. Okay, so because of hydrogen bonding, alcohols have high intermolecular forces. Okay, yeah, it says one. Now, alcohols in general, I'm just saying, have high IMFs. However, if you have a long alkane chain, coupled to the high IMF alcohol, the low IMF chain will take over. I always give this analogy. Who's heard of the Lone Ranger? Raise your hand. No one's,
He said a Lone Ranger.
Lone Ranger. It's like, at first you just say Lone Ranger. Yeah, remember Lone Ranger? Little math, white horse. Who was his companion?
That I don't know.
Remember the Indian guy? Tonto. Now, the Lone Ranger wasn't all that smart. Tonto was very smart. He had Native American smarts to it. So one day, he wanted to prove a point to the Lone Ranger. So he took his quiver of arrows, took one arrow out, said, Lone Ranger, break this. He goes, oh, break it in half. So he gives him 2 arrows, breaks it in half. Then he gives him the whole quiver of arrows, 24 arrows. He couldn't break it. That's because the sum of all the arrows together is strong. Individually, it's weak. So the sum of weak forces, if there's enough weak forces, will overcome a strong force. Like our Revolutionary War. We were weak. British Army comes in, fancy uniforms, lots of cannons, but we were a bunch of people that had a purpose in life. We wanted freedom from that Great Britain. So all those weak forces together ended up being a strong force against that other strong force. So we're going to apply that same analogy to chemicals. So we're going to have a long tail on that OH. Now, each one of those carbons has low IMF. They just have London dispersion force. That's all I got. But there's a lot of them. That OH is very strong. It's hydrogen bonding. Excuse me. So if we have So if we have 7 carbons or more attached to that OH group, that'll make that molecule non-polar because the weak have overcome the strong hydrogen bonding in the alcohol. And this graph shows it. So the breaking point, 7 carbons. Now we're going to see the same thing happens with acids. 7 carbons, breaking point. Because acids are very, very strong IMFs as well. So,
Repeat that. You said if we have 7 carbons or more, it becomes
yeah, the weak IMFs will overcome the strong IMF for the alcohol. But you have to have at least 7. If it's less than 7, it's more, that's more like an alcohol. Once you get over 7 though, that's more like an alkene. And alkanes have weak IMFs. That makes sense? Okay. And we're going to continually see this graph. This graph represents IMF. This is an IMF graph. The stronger the IMF, higher melting point, higher boiling point, and higher surface tension. So you look at this alcohol versus this alkane. Same molecular mass. The alcohol boils at a higher temperature, it melts at a higher temperature, and it has stronger surface tension. You always consider those 3 things when you're talking about intermolecular forces. Now, surface tension is important if you're a mosquito. Because mosquitoes like to land on water and walk on water. That's because the surface tension of water is very, very high. Because it's got two hydroxyl groups, two hydrogen bonds. So it's quite strong. Now, as we cover more and more functional groups, we're going to be adding lines to this graph. And you'll see relatively where each functional group stands relative to the others. Okay. All right, I said alkenes are unstable. Alcohols are stable. That's why it's easy to make an alcohol from an alkene. If we want an alkene from an alcohol, we have to add a lot of energy, high temperature. That is very hot, 180. Very hot. And basically what happens is, this is called an elimination reaction. We're going to eliminate water. We're pulling water off that alcohol. When we pull water off the alcohol under high strict temperature, we end up with an alkene. So when things we go from stable to unstable, it requires energy. If we're going from unstable to stable, it doesn't require any energy. Okay. So now an alcohol can become an alkene. That's a dehydration or elimination. Elimination reaction or dehydration. Dehydration means you're taking out water. Notice though, there's another process that could happen at lower temperature, 140 instead of 180. Okay, so this is the energy here. That temperature. So let's look at an example reaction. Here we've got so this is 1, 2, 3, 4, 5. So this is a 2-pentanol. Let's be carbon 2. All right, and we jack up temperature. Okay, so high temperature and acidic environment, we're going to dehydrogenate it. We're going to pull off water. So, and then mix, you're going to get a mix over here. The reason why you're going to get a mix is there's two ways to pull off water. We have a hydrogen here. And we have a hydrogen here. So here's one way to pull off water. And this is another way to pull off water. That's where we're gonna have a mix. Now, if the OH is on the end, you won't have a mix. Only, that's the only exception. Otherwise, you always have a mix. So that means we've got one pentene, two pentene as a mix. Which do you think is more stable, left or right? You said right. Why? More symmetrical. So Sim wins out here. Markovnikov. Two H's, three H's, that's five total. 3, 3, 6. So Markovnikov also wins. So whenever the OH is in the middle, which it'll be most of the time, you're gonna get a mix. If it's on the end, no mix. Because there's only one way to pull off water when it's on the end. Okay, does this make sense? Well, have you tried one of these on your own yet? Yeah, that's why it doesn't. Okay, so. All right. This is how it works underneath the covers. That's called a mechanism. We're not covering mechanisms in here. Now, instead of 180, we gave it less temperature. That's when we form an ether. So 180, we form an alkene. At 140, we form an ether. So you've got two alcohols. They don't have to be the same. They can be different alcohols. And then on either side of the oxygen will be that backbone of the alcohol you started with. Okay, so if this was so basically we're going to have two backbones, primary and secondary. They can be the same or different, doesn't matter. So they're going to be stuck together by the OH groups. So that's the only time so far that the product doesn't have the same backbone as what you start with. When you're making an ether, because it takes two alcohols. If the alcohols are different, you're gonna have two different backbones. In this case, a yellow and a blue one. Now, naming ethers. Okay, this is the official name. Dipenoxypentane. Okay, that's a real mouthful. We are not going to use the official IUPAC. We're going to say dipentane ether. That will be the preferred one for our class. And this is the part that makes it, this part here refers to this here. And then penta, there's 5 carbons. And we're doing that onto a pentane backbone. Okay, so at 140, we form an ether. At 180, we form an alkene. Okay, my laptop is losing power, so I'm going to plug it in. Okay, one more reaction and we're done for today. Okay. Now this is where the primary, secondary, tertiary comes in. When we oxidize the alcohol. When we oxidize the alcohol, we form, there are 3 different reactions, depending on whether it's a primary, secondary, or tertiary alcohol. We're talking right out here. So when you oxidize an alcohol, if it's primary, it goes to something called an aldehyde. I'll talk about that in a minute. And then that's further oxidized to an acid. If it's secondary, it'll go towards a ketone. If it's tertiary, nothing happens. Okay, so 3 situations. If it's got 2 hydrogens attached to the carbon with the OH, it can be oxidized twice. 1 hydrogen can be oxidized once, no hydrogens, it can't be oxidized at all. Okay, let's talk about aldehyde ketone. aldehyde as the double bonded oxygen called a carbonyl. This is on the end, it's called aldehyde. If the carbonyl group, the double bonded O is in the middle, it's called a ketone. Now that's unit 2's naming. So all you need to do is be able to identify, just say aldehyde or ketone. Naming is very similar, but that's chapter unit 2 stuff. Okay, so primary alcohols, when oxidized, and I'm going to use this in our class. Our first wet lab is on alcohol, by the way. And we're going to be oxidizing them, reducing them, all kinds of stuff. Okay, so what happens in oxidation? We lose a hydrogen. In 305, we lose electrons. In 306, we lose hydrogens. Same process. The oxidation number goes up either way. Okay. And then if a tertiary, there's no hydrogens on that carbon, so it can't be oxidized. So this is what we do in a reaction with a primary alcohol. By the way, on Wednesday, I'm going to start class off with reactions again of alcohols, just as a review. Okay, so if we're going to oxidize a primary alcohol, it has 2 hydrogens. That means it's going to be oxidized twice. First time it's going to go to an alcohol to an aldehyde on the end. And because it has another hydrogen here, it can be oxidized again. That's where it goes to the acid. And this is what happens in your kidneys when you drink alcohol. Your body has some enzymes called alcohol dehydrogenase, which is an oxidizing alcohol enzyme. So it converts your liquor you drank into the aldehyde version. And then there's another enzyme called aldehyde dehydrogenase, which oxidizes the aldehyde to the acid, which is acetic acid, and you urinate it out. Now, certain cultures lack those enzymes, in which case people in that culture will stay drunk longer. Now, aldehydes are very, very unstable. So if you don't have a lot of aldehyde dehydrogenase in your liver, that's when you get cirrhosis of the liver. The aldehydes attack your liver and make it non-functional. Okay, so let's look at secondary oxidation. Okay, so again, we're removing hydrogens. So that's going to go. Notice there's no more hydrogens at that carbonyl group. So it can no longer be oxidized. Tertiary alcohol, there are no hydrogen there at all. So no oxidation. Okay, so we're going to end here. And we'll continue on Wednesday from here.